If you are trying to build your own program, for example, all the messages can be encrypted by whatever encryption protocol you use. So these are all the things you have to take care of in your application layer. Any questions so far? Okay. Right, so if you want to know more about application, you can always spend your time studying these protocols. And then next, we'll move into the next layer. Chapter 3 is about a transport layer. So again, I want to give you a roadmap. So if you need to remember anything from this section, is this protocol stack. We just finished the application layer. That means a message is sent from a source. It will just magically show up in the destination, and it will be received by the client program, or it may not. So next, let's get down into this next layer of protocol stack. That's the transport layer. In the transport layer, all the packet is called segments. Now, of course, if you have more time, we can go to the next layer, the network layer, link layer. But in this section, we'll just stop at this transport layer. The goal is for you to understand what's going on when you do the socket programming. You especially spend a lot of time talking about TCP and UDP socket programming. So the goal is for us to understand the principle behind the transport layer services. This is a few things that they provide: multiplexing, reliable data transfer, flow control, and congestion control. In this course, we will mainly cover the multiplexing and the reliable data transfer. We will not have time to cover these two parts. And we are going to use the Internet Protocol stack as the example. And that means UDP and TCP. I actually mentioned there are also other protocol stacks other than the Internet. For example, when we cover MPI, it is a different protocol stack. Okay, question?
Which 2 points did you say we were not covering? Sorry.
Flow control and congestion
Flow
control.
congestion.
And this is an outline. We'll first go over the service, then hit these points one by one. When you're working with transport protocol, it basically gives you a logic end-to-end transport between two processes. So we are entering the logic here. That means it's actually you get a lot of service from the lower layer of the Internet Protocol stack. But for whatever things you do in the transport layer, it would seem as if you are just talking to the other process directly. So everything, when you're trying to move this packet around the network, is all transparent to you. The details are all hidden from the transport layer applications, transport layer programs. So first thing you need to know is the packet is pushed down from the application layer. So in the sender side, that means the application message is packaged, encapsulated into a segment, and then passed into the transport network layer. So on the receiver side, it takes a packet that's passed from the network layer, then de-encapsulates the segment to message, and then pass on to application layer. So this is the middle layer, just transport the packet from top to bottom, from bottom to top. Network layer is the next layer up below the transport layer. So what is the difference? So in network layer, you have a logic communication between two hosts. The transport layer, you have logic communication between two processes. So one example you can think of is the US Postal Office service. For example, if you put a mail into a mailbox, the mailman will deliver that to a house, right? It doesn't deliver to a person. So in this case, the house is the host, and the process is the persons in the house. So this is the analogy. For example, postman, the mailman will get a mail. It is sent to Anne's house, and then there are 12 kids. Then For example, N should be the transport layer, so provides transport layer for delivering the mail from the mailbox to actually individual person. That's the demultiplexing step. Does this make sense? Okay. And we will have two different protocols. You probably can hear we talk about this a lot. That means this is the two only option you have. And when you develop an application, you will have to make a choice between UDP and TCP. TCP provides you with a reliable in-order delivery. That means whatever message the application receives is guaranteed to be without error, and it will be delivered in the same order those messages sent. But UDP doesn't guarantee that. The message may or may not be delivered, and the mail may not be delivered incorrectly. TCP also provides flow control and congestion control, so that benefits the whole network, but UDP doesn't really care about that. And another distinction is TCP is a connection-oriented service, but UDP is a connectionless service. Neither of them provide any guarantee about the delay and bandwidth. So remember last time we talked about all the expectation you can expect from a connection service, and this is the two other types of guarantees, and none of those two provide those. Okay, so let's get into the first service these two net transport layer protocol provides. That's the multiplex and demultiplexing. Multiplexing is actually pretty simple. Basically, let's say you have a application running here, it sends a message out. What it all does is just to specify, give it a transport header. So this is like if you have a house of 10 people, they all need to send a message. Basically, they give the letter to one person in the house, like the parent. Then the parent will just write down their name, the sender's name. So in the receiver side, they will know which mail comes from which sender. So that's all they do, basically add on the sender's name in the header. So the multiplex means someone will look at the address, then look at who actually is this letter intended for, and then this who is the process, is demultiplex step. This is how it actually works. So remember, we are talking about application data. That's the application layer packet or message. That's the payload of the segment in the transport layer. But then in the encapsulation process, we will add a header on top of it. The first 32-bit is specified as a source port number and a destination port number. So if you remember in the socket programming, we also need to provide a port number. And we'll have 16-bit for the source port and a 16-bit for destination port. That's basically constrains how large this number should go. So last time we talked about is tens of thousands. So it actually just goes to 10 to the 16th number of ports. So the host uses this IP, the destination port number, to specify which process to receive it. So when we set up a socket, remember we can bind a port number to a process. So this is basically how it knows. Specifically for UDP, we just need these two information to do the demultiplexing, the destination IP address and the destination port number. The IP address specifies the computer, so that's given by the IP layer. The destination port number is associated with this process. When the host receives a UDP segment, it uses the destination port number to give this segment to the right process. But if you have the same port number, let's say if you have a web service a port, like in the homework you are working on, it uses UDP. And all of you guys are sending the message to that UDP process with the same port number, 12,000. So in that case, the server actually needs to demultiply. Doesn't know which one of those programs send the message to. So it all goes to the same process. And this is an example. So you have these two kinds here. that it creates this socket, and this is the port number associated with this client process. And this may be another kind with a different port number. So imagine this is all the client program that you're writing now, and this is a server program that's running on in the cloud. So you all can send a message to this server, and when you send this message, the transport layer service will add onto this two information in the header that contains a source port number, which is coming from here, and the destination port number that's corresponding to what's in here. When this server provider needs to reply this message, that's when we give you this message back. Basically, just reverse the source and destination. The source will become the server program's port number, and destination port number will become the source, this port number of the client. So basically, this travels back and forth. When this server program is doing the transaction with another client program, you can also follow the same protocol. So for example, in this case, when a message is sent from this client to this server, the source is the port number is this, and destination port number is this. But the server needs to know that this message comes from this client, so they can reverse the port number and specify that to the destination port number to this, so the message will be delivered to this client program. So that's pretty straightforward. In that case, every port number is associated with one process, one UDP process. And that's also have one mapping between the socket. One socket basically is associated with one port number. TCP is more complicated. So again, you should remember this process. There's a socket and there's a port number. These are three very different concepts in TCP. A TCP socket is specified by 4 tuple. That's the source IP address, source port number, destination IP address, and destination port number. So in contrast, UDP socket is specified by only 2 tuple. It only needs the destination IP address and a port number. So when the receiver receives this TCP segment, it actually uses all this 4 information to demultiplex the message to the correct program. So when you have a process, you can attach multiple port number to it, and each port number can have multiple TCP socket. And that's because each socket can be identified by its own tuple. So for example, if you are a server program, and you ask everyone to send to the same destination IP address and IP port number, but because all this client has a different IP address and different port number, they all have their own socket. And this is a particular example. So we are all using port 80. Like say if you go to Google, it sits on a particular IP address. Many of the people are trying to connect to that server through the same port number. But actually they all have a different, their dedicated connection. That's because all these clients have their own unique IP address and a port number. And this is how TCP demultiplexing works. On the server side, we have let's say a threaded server here. So let's say this server listens to the same port 80. But that port 80 can actually be associated with different socket. So in this example, in this socket is talking to this client program. Let's say it sends a message from this socket to this socket. Then basically you need this 4 tuple. Source IP and source port. So let's say this source IP is B here. We have a IP address B here. The port is 80, but the destination is this IP address of this host here. Then this is the port number for this host. So this is a unique socket number in this host here. But when this host talks to the other host here, with IP address of C, it actually uses the same IP address, source IP address that's in here, the B here. But then because the destination is different, the port IP address here, this is the destination. So this is how you can create a multiple socket from the same port number. So remember, this is not possible with UDP because you only use the two tuple to create the sockets. Okay, so this finish